Welcome back for the afternoon session. I'm very happy to welcome Keshav Aggarwal, who will enlighten us about applications of the delta method.
Thank you, Julia. So last time we had talked about delta methods and then also basically said what a trivial delta method is. And today we are going to apply the trivial delta method to get a wild type subconvexity bound in the T aspect for L functions of holomorphic cusp forms. And the goal of this talk is to essentially show you the heuristics and kind of what goes behind those heuristics, so that when you see these heuristics maybe sometime in the next week, it's not completely a surprise for you. So let me maybe start with saying that our goal is to prove a bound like L1/2 plus IT, like T to the 1/3, where F is a holomorphic cusp form, and maybe let's just take it for SL2Z. And then, as we had said last time, there's an approximate functional equation. And what we can do is do a dyadic partition, so that you have to go only up to the square root of the conductor. The conductor was T squared. It's T raised to the degree. And then you have this thing where the sum that you have to estimate looks like this. And then we said that there will be a smooth weight function that is supported between 1 and 2. So this will make sure that small n goes from big N to twice big N. But we are going to abuse the notation, and a lot of times you are not going to write the weight functions. But we'll have smooth weight functions lying everywhere that have bounded derivatives. Right? So a lot of times what I'm going to do is I'm going to write something like this. And this notation is going to mean that there's a smooth weight function that captures the size of these variables in a dyadic segment. And the next thing I had said was that for a lot of sketch calculations for heuristics, it suffices to take maybe the biggest possible n. So here n goes up to T to the 1 plus epsilon. Of course, if you're not able to get a good bound for the largest n, you cannot really hope to get a subconvexity bound. So for heuristics, that's what we are going to do. We are going to take n to be as large as possible. So what we are going to work with, the object that we're going to work with is going to be something like this. So there's a smooth bump function which captures the size of this index small n, and then we are going to apply the delta method right away. So we have so this was what we had left at the last time. So we are going to now take this up and expand this out by writing out the delta symbol, and then see how we can manipulate these sums and what we can get. Also, what we had said the last time was that if you want to detect an integer is equal to 0, what you can do is you can detect when this integer is congruent to 0 modulo q for some integer q, and also try and detect that the size of this thing is less than maybe, let's say, an x if you have something like this. So as soon as you ensure that the size of this index is less than some parameter, and this parameter is smaller than this other parameter q, by which you take this congruence condition, you are forced to have m is equal to 0. So that's what we are going to use. This is the trivial delta method, and we had written out an expansion for that. We had written out this as so Okay, so another notation when I say this, what I mean is summing over classes A modulo Q. So I'm going to drop the mod sign. This is E an over Q, and then integral of E nx over x is the variable I'm using, and some another smooth function, let's say W1 of x. Dx. And if you do repeated integration by parts, you will exactly get that expression. Right, so this is what we're going to apply, and we will apply this with m is equal to n minus r, because that's what you want to detect. Okay. So let's write everything down. Okay, so I guess there's a typo. Thanks. Here we are. Yeah. We will now do that. So to begin with, this is the delta symbol. But what we are going to do is we are going to take an average sum of these deltas. So thank you. So what we are going to do is we are going to take Q to be primes, say P, and in an interval, well, P to 2P. So we are going to average over all the primes in certain intervals. Okay. So the delta that we're going to use, therefore, as Saurabh pointed out, is going to be, well, so P star is basically P over log P, the number of things that you are averaging over. And then P is going to be something going in a dyadic segment, let's say. And then we have the same thing. Okay. So A n minus R over P and integral of n minus R x over big X. And also for notation, what I'm going to do, you'll see this is going to be a little bit handy. I'm just going to choose, so again, X is a parameter. Over here, the sizes of n's and r's that I'm taking are of size t. So I'm just going to redefine a parameter. I'm going to call X to be t over k for some other parameter. That we choose k, and we will choose this to be something strictly less than t. Okay, so we are going to choose basically big X to be also something strictly less than t, and this k something strictly less than t. All of that means that if you want to detect a delta symbol right here, what we would want is that the modulus that you're taking, so q in this case and p in that case, is something which is bigger than this x. That is to say that we are going to take this p bigger than p over k. Okay. So we are going to now combine this delta symbol with that double summation of n and r, and we're going to write everything together and see what we get. So what we are using is an averaged version of the trivial delta symbol in order to write things out. Okay. Good. So I'm going to first write the expression right here. So what we have to essentially estimate is this 1 over p. I'm pulling out the integral all the way out. We have a sum over these primes. We have the congruence condition detecting A. And then I'm just rearranging these sums a little bit. What I've done is the parameters that come in the delta symbol, I've pulled these all the way out. And then the other indices that are the R and the N index, I'm putting those inside. So the R index is something with the IT oscillation. And you have this. And all right. So of course, there is some kind of a weight function. So this is nothing but a weight function, a smooth weight function, again, bounded derivatives that supports your variable R between Tn to T. And you have the n summation, which is capturing the Fourier coefficients. So I guess I kind of wrote the opposite, so I should correct one thing right there. So I just have to make sure that I also write a weight function, maybe a weight function that captures the size of n. So right now I have written all the weight functions like this. And did I, instead of n minus r, I actually detected r minus n in this. So let me just flip the signs right here and right here. This is the same thing really. And now what we'll do is we are going to analyze the R sum and the N sum separately. So we have this R sum, which does not have the Fourier coefficients. We have the N sum, which does have the Fourier coefficients. And okay, I should also say what the goal is. What do we want to actually prove? So if you look at this particular thing and either apply Cauchy-Schwarz inequality and Rankin-Selberg bound, or let's just put absolute values inside and use the Leens bound. Okay. So if you do that, then maybe I should write right here that the trivial bound that we have is T to the 1 plus epsilon. That's just by putting absolute values inside. Right? And so the trivial bound, if you apply right here, is going to give you the convexity bound for the L function. So we have to do something and get certain cancellations. Also notice that once you write the single sum as a double sum, so once you write your single sum as a double sum, now you have two sums. So you have an N sum and an R sum that are of size T. So if you apply the trivial bound after the application of delta symbol, then the bound is T squared. So you have suddenly lost a full T. So you have to gain a T and a bit more in order to get the convexity, subconvexity bound. So we are going to apply a Poisson summation formula here, a Voronoi summation formula here. And I mean to show you the heuristics and basically why the heuristics work. So we are going to actually write down the Poisson summation formula, try to do some stationary phase analysis, and see that we are able to get to the heuristics. Right? All right. So I'm going to copy the R sum again over here. So I'm not going to write the weight function because, again, my notation is that there is a smooth weight function capturing this index in a dyadic segment. And this is r to the negative it e ar over p, and you have e negative krx over t. Okay. And also notice the fact that here x is a variable which can be something supported between 1 and 2, let's say. Okay. So all of these weight functions are supported in a dyadic segment, in this segment, let's say 1 to 2. All right, so what's the Poisson formula? Recall. Let's say that f is a Schwartz function. I already used f, so let's say h is a Schwartz function. Then you can, of course, take its Fourier transforms. And if you sum over the lattice n over z, all you have is this. So the sum of these f's over a lattice is going to be the sum of f hats over the dual lattice. In this case, it's just that the lattice and the dual lattice both are z itself. And we are going to apply this particular thing while keeping in mind that there is an additive character, modulo p, sitting right over here. So what we'll do is, in order to apply a Poisson summation formula, we're going to do two steps. First, we're going to break the R sum mod p. And then we are going to apply Poisson. So breaking the R sum modulo P means just break it modulo classes. So let's redefine a variable. And did I already use? I did not use alpha so far. Okay, so let's redefine the variable R1 so that R is alpha plus R1P, where now alpha runs mod P and R1 is going to be some other variable. But notice that if R is going to be of size T, then R1 is going to be something that is of size less than that. So something like T over P. Also, the fact that we are taking things to be of in a dyadic segment. So instead of just saying it's less than, I can actually take this R1 to be of size T over P. Okay, let's now write down these calculations. So it's a good idea. So you have the Poisson formula, you have this. So until I erase the board, it's a good idea to actually write R as alpha plus R1P right here and try to get this additive character out of the summation. Okay, so try doing that and then we'll do it together with, these are I'm trying to break this heuristic into small steps so that you can do it for yourself and the heuristic is not mysterious anymore. So let's get this right, R as alpha plus R1P. And what you should notice here is that EAR over P is E alpha, A alpha plus R1P over P, right? And over here, you see that EAR1P over P is just 1. Right, so this cancels out. Now AR1 is an integer, and so now this thing is equal to 1. So this does not have an R1 in it. So you can pull it out of the summation, and what you can therefore write this R1, this R sum as is that what you began with, this is equal to sum of alpha modulo P, E of A alpha over P, and then you have the R1 sum. So R1 is going to be of size T over P, and let's write things. So R is alpha plus R1P to the negative IT. You have E negative RKX. So this is alpha plus R1P KX over T. And then we apply the Poisson summation formula. So here, imagine now it's a summation over R1s. And again, it's a summation not over just a dyadic segment. You can imagine this as a summation over all of it. And there is, don't forget that there is a smooth weight function sitting right here. So I guess for clarity, let me reintroduce that smooth weight function U as it was written over there, right? So if we apply the Poisson formula, right, and you do a change of variables. So when you apply the Poisson formula, you have to calculate this Fourier coefficient. And when you calculate the Fourier coefficient, what you will get is that this R1 goes away and there's a continuous variable that replaces it. That's how you basically calculate its Fourier coefficient. So that what you get is, maybe let me write another step. This is alpha modulo P E A alpha over P, and then you have, let's say the dual variable is called R. So we apply the Poisson summation formula there. So alpha plus YP to the negative IT, E alpha plus YP AX over T, and you have this U alpha plus YP over T. And of course, I'm missing certain integrals. So you want to, of course, do the Fourier coefficients. So E negative RY dy. Right, so this is the Fourier transformation of that function sitting inside, and you are taking its summation. Yeah. There's a minus sign missing. and above. I took it negative. Thanks. It should be a minus sign here and a minus sign here. Thank you. Yeah. Sorry. From start, I had flipped it. Okay, so let me make sure that I am not making that mistake. So should I just keep a minus here instead? Oh, I switched that. Thanks. Like here. Thank you. Sorry about that. So yeah, I should not have had this. And right, I should not. Okay. Now I can do. Okay. So here, two mistakes do cancel out. Okay. Right. So we have this. And let's do a change of variables right here. Okay, so today is this lecture is going to be like very computation heavy, something that you can also try to do along with me and see what you get. There's a lot of basic steps one after the other. You do a change of variables. Let's say u is alpha plus yp over t, and then once you do the change of variables, what you end up getting is t to the 1 minus it outside. You're going to get, because you have done this change of variables, you're going to get a 1 over p outside. There's going to be this alpha summation modulo p, which is e a plus r alpha over p, right? This I have not made a mistake. All right, this is fine. And then you're going to have, the R sum. So the R sum is this something which has this u to the negative it. Inside this, you're going to have negative ax plus rt over p. And you'll have this u. And then, of course, you have the smooth weight function. Let me write it. And you have this. Hey, this is change of variables. And what you get out of this particular p sum is a congruence condition. So this alpha sum modulo p detects a congruence condition. And that's going to be a is congruent to negative r modulo p. Yeah. Again, missing something? So I've done the change of variables, right? Already. Yeah. So that t cancels out. The sum over r is outside. So thank you. I should, of course, take the sum over r to be. Thanks. Good. All right. So we have this. Okay. So now the point of writing all of this a little explicitly is to basically show you where you're getting the congruence condition, and also to go ahead and try to analyze this integral in two different ways. One, if this r variable is too big, in which case we can apply integration by parts. And another, if r variable is a little smaller, in which we use stationary phase analysis. Okay. So the first thing to notice is that you have a congruence condition. And this congruence condition is going to mean something. So we have to be careful about, whenever we apply a dual summation formula, we have to be careful about the zero and the non-zero frequencies. Right? So A was running modulo P, and A is congruent to negative R modulo P. So if A is not zero modulo P, then A is co-prime with P. That will mean that R is co-prime with P. And if R is co-prime with P, R cannot be zero. So the only case when R can be zero is when A is equal to zero. Okay. And therefore, I'm not going to really write it, but initially in the delta symbol, as we had written, we had a certain summation and a certain integral. The analysis of A is equal to 0 and A not equal to 0 have to be done a little separately. Also note that if A is equal to 0, then you don't have this. Therefore, it does not quite make sense to break this sum modulo P before you do all of that analysis. Okay. Therefore, you have to handle those cases differently. And another simplifying assumption that I'm going to make for the purpose of heuristics is that I'm going to take only the case when A is not equal to 0 over here. Okay, so when A is equal to 0, you're already saving the length 1 over P, because there is only, so one of the P many things is 0. So you are summing over only 1 over P many things. So the number of things that you have to sum over is already less, and that analysis is going to be absorbed in the error term. You have to take my word for it. You can check the details later, but we are going to have this assumption right here. And so if A is not equal to 0, that will imply that R is also not equal to 0 right here. So that's one thing. Now the second thing is we have to try and analyze what this integral is. Okay, and what we are going to do is integration by parts. Again, remember that u is a smooth weight function, so that small u is between 1 and 2, let's say. X is between 1 and 2, let's say. So what happens if big R, small r is too big? Right? So if you compare the sizes of these things, what you can do is you can first off write, well, you can combine, let's say, this along with this. So what you do over here is you differentiate u to the negative it, u times u, and you integrate e negative kx plus rt over p times. So when you do this integration by parts, you differentiate this combination and you integrate this one as many times as you want. So let's say you do that j times. Then what you end up getting is that this particular integral is going to be bounded by, so when you take the derivatives, t minus 1, t minus 2, and all that come out. So that's going to give you 1 plus t in the numerator. And in the denominator, you get kx plus rt over p. So this happens if you do this integration by parts, j times. And now notice that if r is big, then the denominator is big, so the fraction is small. So if you take its jth power, that is also going to be very small. Now the question is, how big should r be so that it is much bigger than the numerator? Okay. Now one of the assumptions that we had taken is that k was already less than t to the 1 minus epsilon. So this part does not really have a chance of winning over the numerator. So it's only this part that can win over the numerator. So as soon as r is bigger than p, rt over p is going to be bigger than t, and you will have a saving, right? So if r is bigger than, let's say, p times t to the epsilon, then this whole thing is going to be smaller than t to the negative epsilon j. And if you take j to be big, let's say 1000 or 10 million over epsilon, you have a huge polynomial saving. Okay? So that basically means that you get a saving if r is big. So that just means the r sum is restricted to length less than p times t to the epsilon. Okay. Let me just pause here for a bit. That good. The small x is something which is between 1 and 2. K is a parameter less than t to the 1 minus epsilon. P is a parameter that is bigger than t over k. Right now, I have not said how big p can be or how small p can be. It just has a lower bound on it. All right. So we have this. Okay, so putting all that together, we have this R sum. What that ends up being is that this is equal to t to the 1 minus it, as we had over there. You have an R sum such that the size now goes up to p times t to the epsilon. We have r not equal to 0. And also the fact that you have a congruence condition, A is congruent to negative R mod P. And then you have an integral. And this integral is u to the negative it, e of kx plus with a negative sign, kx plus rt over p, u, and then you have this wave function u du. Right, so this is the transformation that you have. And of course, there is an arbitrarily small error term that you like, let's say this. So you have transformed your summation. Okay. So now coming to the heuristics and basically the way you will see people talking about these things. So there is an original length right here. And once you apply a Poisson formula, which is a dual formula, you get a dual length. And there's a very nice way of getting the dual length out of the original length. The dual length is going to be the conductor over the original length. So it's the conductor of the sum, not the L function. Okay, so this is conductor of the R sum. Okay, and now we want to see what the conductor of the R sum is. How do you calculate conductor of summation? For that, you have to basically look at the oscillations. You have to look at the Archimedean part and the non-Archimedean part and take the product. So basically, you're looking at all the places and seeing what the adelic norm is essentially. Right? So you take all the Archimedean and non-Archimedean norms together. So the non-Archimedean norm right here is only captured over here. This is no, green over green, not a good idea. So this is an arithmetic oscillation. So all the non-Archimedean oscillations is what we call the arithmetic oscillations, and all the Archimedean oscillations are what we call the analytic oscillations. So we have this r to the negative it, this is the continuous variable t, and you have er kx over t. So these two are the analytic oscillations. The size of the arithmetic oscillation is the modulus of this additive character. The modulus of this additive character is p. So the arithmetic oscillation is going to be of size p. In analytic oscillations, you cannot really say that there's a modulus t of this character. This is a continuous variable. So the size of this analytic oscillation is basically going to be the size that you have here and the size that you have coming from here. And then you have to basically compare the sizes. Okay. The size coming from the IT oscillation right here is going to be of size t itself. And the size that you have coming from here is going to be of the size of this whole thing sitting inside. So it's going to be the size of r kx over t. The size of r to begin with was t. So the size of r kx over t is going to be t times k over t, which is t. Okay. But we had the simplifying assumption that k was less than t, and so this is of size t. And so the net conductor is going to be the product of these things. So the conductor is going to be the product of these things. And therefore, that gives us the dual length. The dual length, therefore, is going to be, let me write it over here. The dual length is therefore going to be p times t divided by the original length, which is t. And of course, in order to make sure that you get some polynomial savings in the error term, you introduce a t to the epsilon. Okay. But this calculation was to basically show how you get this. Because a lot of times you're going to see people say that, all right, you have a certain conductor of the certain sum, and you get this dual length. Okay. This is how you get the dual length. Okay. t to the 1 plus epsilon. Yeah. Okay, good. Yeah. Good. Okay. Right. Yes. Thank you. So the arithmetic oscillations are multiply, and so if there was another oscillation, it's going to multiply. They're going to multiply together, and the analytic oscillations are basically going to add together, and the final conductor is going to be the product of all of these things. And again, the way to imagine this is like if you think adelically, then you have an Archimedean place, you have all these non-Archimedean places, and the total adelic thing is a product of all of these things. Right. So you have the analytic ones that you are adding together and then multiplying with all the non-Archimedean ones. Okay. Okay. Now the second non-trivial thing that I want to show you, which is actually a good part of all of these calculations, is the stationary phase analysis. That is, we have to look at this integral. So we just looked at this integral in a rather trivial way when this index r is big. We also want to look at this integral when this index r is not too big. I will do this and then we'll take a break. Okay. So let's do that calculation. And see what you get. So you have this integral, which is u to the negative it, e negative ax plus rt over p, u, and the weight function right here. And for this, we are going to use the stationary phase lemma. There are, of course, you can see there's one due to Huxley. Of course, there's one due to a much more powerful one by Blomer, Kahn, and Young. But we are going to state something which is good enough for heuristics. So what we are going to do is we are going to consider an integral that looks like, let's say this integral is I, that looks like e to the 2 pi I fx gx dx, where f, where what do we have? Where, let's say, f is at least twice differentiable continuously, where you have this function g, which has, let's say, smooth. It's a Schwartz function. And let's say that the derivatives are nice. This is going to be good enough for heuristics. Yes. This t to the epsilon. So we are just making sure that we get a polynomial kind of bound right here. Rather, we get arbitrary savings in t right here. So if you look at this calculation, when we do integration by parts, we want to make sure that we are not just getting this bounded by 1, because you don't want to just get powers of 1. You want to get negative powers of some t. So if you just make sure that this r is a little bit bigger than the numerator, then you're good to go. So that's why this extracted the epsilon. See, at the end of the day, in our goal, we just care about the final exponent saving. We don't really care about the logs. So we can be a little relaxed with t to the epsilon here. Okay. Anything else? Right. So let's consider an integral like this. And we are also going to make a few more assumptions. So let's say that x naught is such that f prime of x naught is equal to 0 lies in support of G. Or okay, to be even simpler, let's say x naught is the unique real number such that you have that the derivative vanishes at this point. Right, so this is the stationary point. Then what you have, and I guess again a simplifying assumption that the double derivative, the second derivative, is not 0. Then your integral is going to be asymptotic to I times e to the, well, e of fx naught, g of x naught divided by square root f double prime x naught. And there is, of course, some error term that is going to be very nice and bounded as long as G is bounded nicely. Yeah, you can basically get a very good error because of them if you make sure that this F is even more differentiable and G is anyway Schwartz. So you can actually get arbitrarily small error. You can write more terms in this main thing, and you can make sure that the error is as small as you want.
From the derivatives of.
So here I have just made sure that, yeah. So, but here for this analysis, if you can, for example, make sure that the second derivative does not vanish, that should be good enough, because the error term that you actually get over here will look like this, and then plus lower order terms. So, yeah. In this case itself, like I'm just writing you out for you what the first term of the error term looks like. Say again, please. Yeah. As what Huxley did. Yeah. Yeah. Okay. So let's do this. Let's compute this and say again. 1 plus I over 2. Well, there is an E 1/8 plus fx naught. Right. But then that is, yeah, which is E I.
Depending upon the sign of the
Sign of, right. Right. So 1 plus I by, yeah. Thanks. Right. Okay. So let's just calculate this particular stationary point just to get a flavor of the kind of calculations that we have. And then for the other sum, the n sum, we are going to do the heuristics. Okay. And then get along with what you have over here. So let's just show these calculations. Let's calculate a stationary point. Okay. So what you have here is this particular function. So here you can take all of this to be your function f of u right here. And this is your g of u right here. Okay. Let's write this u to the negative it as e negative t over 2 pi. Oops. Negative u over 2 pi. Okay. We want u to the it. So should it be the opposite? Did I do something wrong? Oh, yeah. Okay. Right. You have this for u to the negative it, and then you have e negative kx plus rt. So of course, I should not be writing this e because this is f of u function. And then you have minus kx plus rt, kx plus rt over p. See? Right. Okay. And let's take its derivative and set that equal to 0 and see what you get. So let's take its derivative. And what you get here is negative t over 2 pi u. And over here, what you have is minus kx plus rt over p. And you want to set this equal to 0 in order to get your stationary point. And let's call that stationary point to be u naught, as we had done over here. So if you calculate what your stationary point is, it's going to be u naught is going to be your negative t over kx plus rt over p, right here. And now one should also check that the stationary point might lie inside the support of the weight function. But notice over here, if you take what the absolute value of u naught is, this is right here. But the size of the denominator, because r is less than t, the size of the denominator is also of size t. And so this is going to be of size 1, which is inside the support. Of course, if you have that r is too small right here, then you will have u naught to be much bigger than the size of 1, in which case you will not have the stationary point lying inside the support. In which case you will have to use not this, but you will have to use, if otherwise, you'll have to use a bound, which is like the first derivative test, something like this. The minimum of u in the support of your weight function. So you have that. Okay. Right. Okay. So I guess I should write down finally what you have. We should also calculate the second derivative. If you calculate the second derivative right here, you have t over 2 pi u squared. U now is of size 1 because that is the support, and therefore the size is going to be of size t. Okay. So what we get after all of this analysis is that the asymptotic is going to have something like 1 over the square root of t, and you're going to write this e to the 2 pi I fx naught or fu naught, where you have to put u naught right here. So if you do all of that, then I can write it for you, what you get. Okay. So what you get from here is that this is asymptotic to, let's say, let me just write a box over here, 1 over square root t. And let me make sure that I write the right correct thing. You get kx plus rt over p to the negative it. Over here, this is something of modulus 1, not depending on x or not depending on r. Okay. So the point of this analysis is two things. First, when you do Poisson summation formula, you will get a dual length, which is conductor over the original length. Your additive character becomes a congruence condition that I erased. And this integral, you'll have to do a stationary phase analysis. A priori, if you just bound it by trivial, like absolute values, and you kill the oscillations, this integral is of size 1. But if you do the stationary phase analysis, you get a square root saving. A square root of what? So the square root of the size of oscillation. Right? So it tells you that the size of this integral is actually 1 over square root t, but you still have certain oscillations that can be exploited later. You still have this x oscillation. Okay, good. So let's take a 5-minute break now, and then we are going to do the Voronoi formula in heuristics. I'm just going to tell you the Voronoi formula, but then I'm not going to tell you all these details. I'm just going to write the heuristics and what the stationary phase gives you. And then, yeah, we'll try to finish it by 45. Okay. Yeah, we have a 5-minute break, right? And we had a negative with that. So we had negative NA over P, right? And you had this E K N X over T, and then some other weight function right here. Right. And then one thing that one must notice. Oh, is it not on? Hello? Can you hear me? Is this? It is not muted. Okay, this looks. Yeah. Okay. Okay, I think it was just not placed correctly. Okay, right. So now we have this n sum, and notice that there was a congruence condition that is congruent to negative r modulo p. So right here, you see that if you plug in a congruent to negative r mod p, what you get here is e and r over p. And since A was not 0, R is not equal to 0, right? And also the fact that R and P are co-prime to each other. And the dual summation formula that we apply over here is the Voronoi formula. Again, this is for now, for the purpose of this talk, I can only use this as a black box. But the Voronoi formula is, make sure that I write things correctly. So if you have, let's say, what's the Voronoi formula telling us? So let's say that you have certain Fourier coefficients. These can actually be coefficients of mass forms and or even Eisenstein series, and you have a Voronoi formula. And let's say that you have a certain modulus C and a certain A, which is co-prime with C, and you have a certain weight function, let's say. Then the Voronoi formula is basically telling us that that is equal to 2 pi I to the k. And then, so again, I'm just going to write this without the good normalizations. And on the other side, what you get is the dual Fourier coefficient. In this case, it's going to be itself because we are taking forms for SL2. Instead of A over C, you get a negative NA bar over C. And over here, you get a transform with a Bessel function. So you have a Bessel function of weight k minus 1, 4 pi square root nx over c squared. And here, this integral goes from like this. And I must tell you what this is. This is a J Bessel function of weight k minus 1. I'm not really telling you why that Voronoi formula comes from. All I can say for now is that if you apply a functional equation for a twisted L function, where the twist is coming from the additive character, then you can get this particular Voronoi formula, get this particular summation formula. Okay? What we are going to basically need for this analysis is an asymptotic for the J Bessel function. So the Bessel function has an oscillation that looks like e to the ix. It has a weight function like this, and plus you have e to the negative ix, and another well-behaved weight function like this. And the weight function satisfies some nice properties. So the derivatives of this weight function, so this is 1 over 1 plus square root x for j bigger than or equal to 1. So you have these things. Say again? Oh, root x I have already taken. Thanks. So you just have this. And of course, depending on the weight. Right. Actually, for j bigger than or equal to 0. We have this. Okay. So in order to do an analysis of a certain summation like this, we are going to use the Voronoi formula. And instead of the Bessel function, we are going to basically look at one of these things, because the analysis of one factor and the other factor is going to be extremely similar. So we have to divide by the square root of the size of whatever is inside. And you have to think, you have to make sure that the oscillation that you're looking at is like e to the ix. Okay. So let me just apply this for you and write what you get on the other side. Right. So what you get, if you apply the Voronoi formula here, maybe let me call this as n sum. And what you get here is that the n sum is equal to, again, your 2 pi I to the k t over p, a summation of n. I have to see how big this is. there is a dual coefficient, and you have E negative NR bar over P, because over here you had E NR over P. On the other side, you will get NR bar over P. And you can do that because R and P are co-prime, because A and P were co-prime. And you have then an integral. So this kyx is coming because of this. I've already done a change of variables. I've put x as x times t, so that or y as y times t, so that cancels. There's a weight function, and then there is the Bessel function, but then the Bessel function is going to have a certain size. So we are going to take that out. So it's p squared to the nt 1/4. So the 1/4 is coming because of the square root of the size, right? So you have that. And then you have the oscillations. The oscillations look like E square root, well, 2 square root Tn over P. And then, of course, you have times square root Y. And then you have Wy. Okay, the upshot being that the additive character becomes a dual additive character, and the analytic oscillation gets you a Bessel transformation on the other side. And you have to do this analysis now. And now I'm not going to do this analysis, but what you can do is observe that if n is big enough, then again you can do integration by parts. Okay, how can you do that? So this is just the size. You don't have to care about this. But what you can do is you can, for example, combine these two together, and you can differentiate these factors, and you can go ahead and you can integrate these factors. Maybe you can change the variable y to y squared so that you can easily integrate and differentiate. And then if you do that, you will end up having a bunch of k's in the numerator and a bunch of these in the denominator. So if n is big, the denominator is big. That means the fraction is small. That means the integral is small, and you get a saving. Okay, so that just means that if n is too big, this whole integral is small, and the size that it's going to be is, again, the philosophy. It's going to be conductor over the original length. The original length was this. The conductor, the way you calculate now is going to be arithmetic oscillation and analytic oscillation multiplied, but it sits with the GL2 coefficient. So you're also going to square it. So the conductor is going to be P times T whole squared. Okay. So let me just write that the dual length here is, sorry, not T, P times K, because over here, N is of size T, sorry. So this thing is of size K, which is KT over T. So P times K, thank you, whole squared. In order to actually explain this heuristic, what you should observe is that there's a square root right here. Because this n is inside the square root, if you just write the fraction, you will have a bunch of these fractions with the square root n in the denominator. So you'll have to square these things, and you will get that square. Okay, so that's your dual length. Okay. And the second thing that you have to do is you have to do a stationary phase analysis of that integral. Okay, so in order to do the stationary phase analysis of this integral, again, you need to do the same thing. You want to look at the function of oscillation. So this oscillates, and this oscillates, and this is the weight function. So if you do the stationary phase analysis of this integral, let's maybe write this as E of fu, or maybe E of fy, wy, dy. Then the function f of y that you have is kyx plus 2 square root tn over p times square root y. And again, you can differentiate, and you can see what the derivative is and when it vanishes. So now this is a derivative with respect to y. So this is this plus square root tn over p times 1 over square root y, and you want to put that equal to 0. Okay. And now observe what's happening here. The size of n is going to be smaller than p squared k squared over t. Okay. So the size of tn is going to be smaller than p squared k squared. You take the square root. So the size of numerator is less than p times k. You divide by p. So this size is going to be less than k. Okay. That just means that kx plus something like k over square root y is equal to 0. And the question is, can that be possible? Well, yes, that can be possible. Because again, it will just mean that y has to be of size 1, which is definitely inside the support of this integral. Again, if it so happens that n is too small, then you will not have a stationary point, in which case you have two advantages. So you have one advantage, that is n has a smaller size, and you can then use a first derivative bound in order to bound this. Okay. Good. So we also should calculate the second derivative in order to see what the saving is. So let's do that. If you look over here, let me just take this space and write the second derivative. Not too hard to see that if you differentiate, that goes away, and you only get a derivative over here, so that you get the derivative like what? Negative square root Tn over P y0 to the 3/2 and a 2 right here. Right? That's your second derivative. And now y naught is of size 1, right? It has to be in the support. And then you have to see what all of that size is. Now that whole size is going to be, again by the same logic, is of size k. Now this thing is of size. So if you look at f double prime y naught, it's going to be of size k. Okay. So if you look at this particular integral transform that you get, you will have an oscillation and you will have a certain saving in size. The saving in size you have is 1 over the square root of that. So if you do that, what you end up getting, therefore, is that the n sum instead transforms as, oops. So I'm almost out of time. So let me just write that this sum is going to be something like some constant p over p square root k and a double second sum, which is of size p squared k squared over t. And then you have lambda fn bar, you have e negative nr bar over p, and then you have a certain integral, and it's asymptotics. And if you want to check later on, I'm just going to write its asymptotics for you so that you can see what it is. It will be a certain integral, and this certain integral is going to be asymptotic too, because I have already normalized by the square root k. It is going to be e negative tn over k e squared x. This is what you have. Okay, so at this point, let me just do one thing. Let me write out what you get so far. So what we have done is we have applied dual summation formulas and done the stationary phase analysis of these integrals. So if you collect all of it, let's just see what you get and what the size of that something is. And I'm just going to indicate what we do next and leave it at that because we are out of time. And I'll just tell you the heuristics of that, the sizes of those things. So after Poisson and Voronoi, the original thing that you started with is going to transform like this. So it's basically going to have t to the 3/2 over pq. Well, let's see if I'm able to actually give you a little more light. I'm able to tell you a little more about what's happening and why it's happening. So let me write a t here. Okay, let me start with writing a p squared here. So you remember that there was a delta method. The delta method had a 1 over p, but then we were averaging a delta method of length p. That's why you were getting 2 p's or p squared in the denominator. So this p squared comes in because of the delta method. Then because of this Poisson formula, you end up having a t to the negative 1 t to the 1 minus it. That's why you have a t over here. And then in that Voronoi formula, you have another t divided by p. Okay. In the integral analysis of the Poisson formula, you had a 1 over square root t, and the integral analysis of the Voronoi formula, you had a 1 over square root k. So this is the sizes that you end up having. And then you have a certain n sum, which is going to be of size p squared k squared over t, lambda fn. and you're going to have a certain R sum, which is going to be of size P. And you have, of course, a certain P sum. So you have this, and then you have certain, right. And of course, what else? I should write this oscillation NR bar over P. And of course, you have all of these oscillations from integrals that we just calculated. So these were the oscillations in this from the calculation of stationary points. So if you look at the sizes at this point of time, what you will see is that all of this size, so you can just bound integrals by 1, you can bound this by 1, this is P, so that cancels this out. And let's use just the way the bound. So let's bound this by 1. So if you just take all the sizes together, the size that you get right here is t to the 3/2 over k to the 1/2. Just by putting an absolute value inside and seeing. Now the point is that right here, is this? There's a p as well. Yeah, there's also a p. Just a second. Oh, wait a second. Yeah, okay, no, this is fine. Yeah, so far what we got here is k was going to be something which is strictly less than t. Right? So if you take k to be as big as t, you will only get t times p, which is p worse than the convexity bound. Okay. So you are quite off from the convexity bound. So I'm just going to say a few last things, and then I'm going to stop. What we will do next is break the structure of this particular summation. So one thing to notice is that I've again not really said more words on this, but Voronoi formula and Poisson formula are involutions. So if you apply Poisson formula twice, you get back the same thing. If you apply Voronoi formula twice, you will get almost the same thing back. So you really cannot apply these dual summation formulas again. So what you can do is you can convert this problem from a GL2 problem to a GL1 problem. So you are going to take out, you're going to apply Cauchy-Schwarz inequality and take out this n sum. So what you do is, right now, you apply the Cauchy-Schwarz inequality. And what you get here is that all of that is going to be smaller than a certain factor that is right here. And you have p squared, k squared over t, lambda fn squared square root times n going up to p squared, p squared, k squared over t. And inside the absolute values, you have the R sums. Of course, I should first write the p sum, maybe that makes more sense. You have the p sum, you have the R sum. Going up to size p, you have this oscillation, and you have certain integrals, oscillations from integrals. And you want to square it, and you also want to then take a 1/2 power. Okay. So what that does is, first off, you can use the Rankin-Selberg bound, and you can say that all of this is bounded by the length. So p squared, k squared over t times to the 1 plus epsilon. So what is inside is bounded by length to the 1 plus epsilon. That's your estimate from Rankin-Selberg theory. And also the fact that you have gotten rid of the Fourier coefficients right here. So you have changed the structure of the n sum. So the next thing that we do is actually open the absolute value squared and apply a dual summation formula to the n sum. And now all you have to do is apply a Poisson formula to the n sum. And now when you apply the Poisson formula to the n sum, you're not going to get back the original object because the Fourier coefficients don't exist now. Okay. So you have to be careful about the zero frequencies that on the dual side, what you get for n is equal to 0, versus what you get for n not equal to 0, because there you had a certain condition that made r not equal to 0. That's not going to be the case here. And maybe let me just write. There's a nifty thing that happens. After all of this analysis, the bound that you get turns out to be actually independent of the parameter p. The bound that you end up getting is like t to the 1/2 times k to the 1/2 plus t over k to the 1/4. This comes from the n is equal to dual n is equal to 0, and this comes from the dual n not equal to 0 contribution. And this is just, in this particular problem, it so happens that it turns out to be independent of this parameter p. So you have to just choose k and you get your bound. Yes, you had something. Something is wrong. This one. Where? The less than bound? Oh. So say again. Root t times k to the 3 over 2. Oh, there's no k in the denominator. Oh, right, because there's a k squared up top. Wait a second. Yeah, okay. So I'll have to, I'm sorry, yeah, I messed up with the this heuristic, but let's see where I'm getting that k in the denominator. But okay, yeah. 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 So I guess there is going to be more savings, but I'll have to check this factor. I think I did not write this correctly, but you will end up having quite a bit of savings from this initial analysis as well. So yeah, okay. So yeah, let me stop at that.